So let's first just try to see what's going on. I'm going to pick some numbers. I'm going to say D is maybe 3, and it's got to divide both A and B. So let's see, a number divisible by 3, maybe 18, another number divisible by 3, maybe 12. And so they're saying that I can write 18 as 12 goes into 18 so many times, so 12 goes into 18 once, right, with the remainder of 6, right? And so I was like, hey, yeah, D divides 6. This is good. 6 goes into 3. That's happy. And it kind of makes sense that D would divide R, because if D divides A and B, then A and B are both multiples of, like, whatever D was, in here 3. So if you keep going up, D would divide all of these, and so if you subtract them, you would still get a number that would be divisible by 3. So if I did like 15 minus 6, I would get 9. That's divisible by 3, because it's jumping up by 3 every time. So the theorem does make sense if you sit and play with it. And so now that we kind of have an example that works, some of these don't make any sense at all, right? Like D divide N? N in this case was 1. 3 doesn't divide 1. There's no reason that D would ever have to divide N. So that guy's out. D is the greatest common factor between A and B? Nah, right? The greatest common factor between 18 and 12 would have been 6. And D doesn't have to be 6. That's just silly. Now, D divides A times B, this is true, but it doesn't help you prove it. But D dividing A minus B, this is what you want. Because if D divides A times B, it kind of makes sense, because if D divided A, then of course D divides A times B. That's just kind of like a no-brainer. This one here has a little bit more substance. This one here is what you would, if you wanted to prove it somehow, then this would be the only one that would make sense. Now, I'm going to say that the book's answer is bizarre. Like, to me, I'm not a super number theory person. If I were to prove this theorem, I would prove it this way. I would not prove it with this. The book still doesn't make sense. I'll do another video if it starts to make more sense, but we can do it just by process of elimination. If I wanted to prove this, I would say, hey, okay, I know that D divides A, so that means that A is D times some number, I'll call it P. And then if D divides B, that by definition, then B is D times some number, integer, I'll call it Q. And then plus R. And so if I solved for R, I'd get R is dP minus N times dQ. And if I just factored out the D, P minus, factored out the P and Q, then hey, R is D times something. I know this is an integer because P I defined as an integer, N has to be an integer, and Q has to be an integer, so this whole thing is an integer, and so our remainder is divisible by D. It equals D times something. So this is how I would go about proving it, which seems very straightforward. I don't know why the answers go proving it this way, but we can still, just by kind of playing around, pick some more numbers, pick different values of D and A and B, and you'll be able to see why none of these make much sense, and that if there has to be an answer, this is the only answer it could be. So if you want to play on your own, let's say like D was 5, A was 200, and B was 75 or something. Try it, figure out what N and B and R would have to be, and see what you think. Again, number theory, not my biggest forte, and so when I looked at it, I didn't quite know what to do, but then as soon as I started plugging in some stuff, I'm like, oh, no, I guess it's got to be that one. So a little bit of a letdown, but it's okay, not too bad.